Since lesson 39 is such a long one, we're going to just talk about the radian measures today, and then we'll talk about the other forms of linear equations tomorrow. So, to start us with radian measures, I just want to begin with a question. If the radius is equal to 1, how far is it around the circle? If the radius is 1, how far is it to go all the way around the edge of the circle? What's the perimeter? Everybody? 2 pi. So, this is how I think it's the easiest to learn and remember the radian circle. We'll talk more technicalities in a minute. But if we started at 0 like we're used to doing, and went all the way around the circle, 2 pi would bring us back where we started, right? What if I go halfway around this circle? How far is that? Everything else I'm going to fill in now is just fractions. So you just told me the top half of the circle is pi. What if I only go half of that? How far have I gone? I've gone pi over 2. So every 90 degrees is pi over 2. And 2 pi over 2, 3 pi over 2, so I'll put that down at the bottom. And then I'm back at 4 pi over 2 or 2 pi. Are we good with those numbers? Okay, let's keep going with fractions. If it is pi over 2 to get up to the top, how far is it if I just go half of that? What's half of pi over 2? Just shout it out for me. Pi over 4, everybody comfortable with that? That's a fourth of pi? So, that means what I'm used to thinking of as 45 degrees is pi over 4. So pi over 4, 2 pi over 4, yeah, that simplifies to pi over 2. 3 pi over 4, that's halfway between pi over 2 and pi. And then I'm at 4 pi over 4. And then if I keep going, that would mean halfway between pi and 3 pi over 2. Let's see, I'm at 4 pi over 4. So 5 pi over 4, 6 pi over 4 at the bottom, but that reduces to 3 pi over 2, and 7 pi over 4. Thumbs up, thumbs down, are we good with those numbers? It's just fractions. Okay, let's go back up to the top half of the unit circle. The whole top half is pi, right? That line out of our way. So what if I split the top half up like this? Have I just divided the top half into equal thirds? I'm used to thinking of it as 60, 120, 180, so yeah, those are equal. So if the whole top half is pi, 1/3, so pi over 3, 2 pi over 3, 3 pi over 3 is just pi. I can keep going down the bottom half of the circle, and I have, so that was 3 pi over 3, so this is 4 pi over 3, 5 pi over 3, and 6 pi over 3 has me back at 2 pi. Oh, there's 4 spots left we haven't filled in, right? We're almost done. Let me go back up to the top half. I am used to, this line is 30, which is half of 60, right? So what's half of pi over 3? Everybody shout it out. So every 30 degrees is just pi over 6. I'm going to fill those 2 in on the left, thinking about it 2 different ways. Do whichever way makes the most sense to you. Every 30 degrees is pi over 6. So pi is 6 pi over 6. This one up here has to be pi over 6 less than pi. So it has to be 5 pi over 6. And if I come down here, it has to be pi over 6 more than that. So I have 5 pi over 6, 6 pi over 6, 7 pi over 6. If you prefer, you could have said, this one is pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. 6 pi over 6, 7 pi over 6, and you could get those that way. This one is pi over 6 before we get to 2 pi, so who can tell me what that has to be? 11 pi over 6. Those are your radian measures for angles. And to me, this is the easiest way to learn them, to think about them, to keep straight which one is where. To think about if it is my unit circle, my perimeter is 2 pi, and everything else is just fractions. If it does not have a degree sign on it, it means radians. So we need to be really careful that we always get that in there. Let's do one more unit circle real fast, which is just going in the negative direction on the radians. And I'll pull that back down in a minute, but I think it's easier for you to fill it in if you start at 0 and go down. And just remember to put a minus sign in front of each of them because you're going in the negative direction. So the pi over 6, pi over 4, pi over 3. You can just copy it, or you can think about the fractions again as you go around and write those in. So let's think a little bit about what is a radian. Because I want any one of these angles to be the same measurement, no matter how big the radius really is or isn't. Just like it doesn't matter if I have a teeny tiny circle or a great big circle. If I'm at this angle, I want to still be at this angle, no matter how big the circle is. So let's think about a little more technical meaning of what a radian is. You'll really work with this more next year, but just to start introducing the idea. All the way around the unit circle once, there are 2 pi radians, right? That's what we just figured out. If pi is 3.14 and so on, 2 times that is a little bit more than 6, right? So there are a little bit more than 6 radians all the way around the unit circle. I'm not putting a pi in that when I'm just saying that. That means 1 radian, not 1 pi, 1 radian is a little bit less than 60 degrees. If I have to get a little bit more than 6 of them all the way around, each one has to be just a little bit less than 60 degrees, right? A radian is just another way of thinking about how much do you rotate. You started our 0 x-axis position, and you rotate how far around do you go. So this needs to be just a little bit less than 60 degrees. And if I drew an equilateral triangle here, I'd be looking at the 60, 60, 60 degrees, something kind of like that. If I curve this side just a little bit, but it's still just as long as the 2 sides that are radii, since it's curved, it's going to have to make the angle come down just a teeny tiny little bit. So 1 radian is when the length of the arc is just as long as the radius. So it's almost that equilateral triangle. And it doesn't matter how big or small the circle is, that angle needs to be 1 radian in terms of its measurement. That angle is still just as big here, even though I am now looking at a much smaller radius and arc length. Same thing if I moved a bigger circle or one that's even bigger than my original circle. Those angles all need to have the same measure, whether I'm measuring them with degrees or with radians, but it's just the amount of rotation so that the arc is just as long as the radius. And that's all we really are doing with that more technical understanding of it, and I'll get really more precise next year with it and do a lot more with it. Okay, one thing we sometimes want to do is to convert between degrees and radians. When we start doing angular velocity farther on into the book, that's when we'll really need to convert. When we're just evaluating, I don't really want you to take the time to convert. I want you to get so familiar with that unit circle that if I tell you 4 pi over 3 radians, you just stop and think, oh, I know where that is on the unit circle, so now I can figure out the sine, cosine, or tangent there. But when we do these angular velocity problems, we'll need to convert. Unit multipliers just mean we multiply by 1, so numerator, denominator have to be equivalent. We know 360 degrees and 2 pi degrees are the same. So 1 in the numerator, 1 in the denominator, except if we simplify, all we really need is 180 and pi are the same as each other. So we would have these 2 unit multipliers that we can use. Now, when you have ones like these, I really don't want you to use the unit multiplier and convert. I'll do it both ways just to show you that it does work. What I really want you to do is to think about that unit circle. Oh, if it's pi over 4 radians, where does that mean I am on the unit circle? We know pi was halfway around, so a fourth of that would put us right here. Oh yeah, if I am right there in the unit circle, how many degrees is that? 45 degrees. Now, if you needed to do it with the multiplier, you could say we had the pi over 4 radians. We want to get rid of radians, so we're going to put radians in the denominator, so they'll cancel out. Degrees in the numerator. The pi's would cancel, and 180 divided by 4 would be 45 to give us the 45 degrees. Similarly, if we had 135 degrees, we know that's right here in the second quadrant. And in radians, we now know if the top is pi over 2 and the left is pi, this was what? 3 pi over 4. If we did it with the multiplier, we would have had the 135 degrees. We want to get rid of degrees, so we put that in the denominator. We put the pi in the numerator, and 135 over 180 would reduce to 3/4, so we'd have 3/4 pi. On for the last one. Does anybody remember where 11 pi over 6 was? Molly? It was almost all the way around at what we're used to calling 330 degrees. So whichever one you have, I just want you to think about first that on the unit circle. What do I need for the other way of measuring it, or for the sine, cosine, tangent there, whatever the problem is asking for. But again, we could have said this was 11 pi over 6 radians. We want to get rid of radians, so that goes in the denominator to cancel out. 180 in the numerator. 180 over 6 is 30. 30 times 11 gives us the 330 degrees. I'm going to go ahead and do this one next. Let's just evaluate some. So if I want to evaluate this, when you have ones like this, I do not want you to write it down on your paper or on the test. That's the cosine of this many degrees. I want you to look at the radians and figure out where are you on the unit circle. What is the sine, cosine, or tangent at that position? So for the negative 25 pi over 6, that means I'm going this way. When I have these ones that are more than once around the unit circle, here's what I do. I count by half circles. In this case, I'm dealing with 6, so I'm going to go 6 pi over 6, which brings me around halfway around the unit circle. 12 pi over 6 brings me back where I started. Keep going in the negative direction. 18 pi over 6, I'm not there yet. 24 pi over 6 puts me right here. I'm almost where I need to be. I just need to go one more sixth, which puts me right here. Everybody good with that's where we are. I don't mess with thinking about how many degrees is that. I think about, oh, I want cosine. It's cosine x or y, everybody. So if I'm on the right side, is my x positive or negative? So for my x's, I'm thinking about these x values. What's this one that I need right here that's close to 1 but not all the way there? Positive root 3 over 2. So that's how I evaluate this. That's all I need to write down. Sometimes on my paper, I'll just do this. I won't really mess with drawing a circle. And I'll just do the 6, 12, 18, 24 pi. Oh, I'm right here. I might write that much down as I'm evaluating it. Okay, now let's do minus 2 times, and now whatever we get when we take the tangent of 4 pi over 3. This time we're going in the positive direction because it's positive 4 pi over 3. 3 pi over 3 brought me here. I need to go 1 more third, which is going to put me right here. Now I need tangent. Was tangent positive or negative in that quadrant? Oh, so it's positive. Students, only sign. Take, so tangent's going to be positive here. Do you remember your tangent values off of that tangent unit circle? They always have plus and minus 1 when we're right in the middle because we get root 2 over 2 over root 2 over 2. This one was going to be the root 3 over 3, and this one was going to be the root 3. So we fill that in here. These are both root 3's, so they are like terms and must be put together. So I have to get a common denominator to do that. So I have root 3 over 2 minus that 2 root 3, but to get the common denominator, I need to multiply by another 2 over 2. So I have root 3 minus 4 root 3 all over 2, or negative 3 root 3 over 2. That makes sense to everybody. Now let's do one more like this. Same kind of thing. This time we're going less than 1 time around the unit circle for both of those. So I need to keep 4 times whatever I get for the sign of pi over 4. So pi over 4. I start here. I'm going in the positive direction. Is this where I end up? What is my sign there? Sign's the y. Root, so positive, root 2 over 2. Then I need plus the sign of negative pi over 3. So now I need to go in the negative direction. And let's see, it's pi all the way over here, so I'm going a third of that. That means I'm ending up right here. Sign, will that be positive or negative here? It's the y, and we're down below, so it's going to be a negative. And who can tell me negative how many? I'm close to negative 1, so negative how much? I'm hearing mostly negative root 3 over 2. Everybody good with that? Okay, those are 2 different square roots, so they aren't like terms. I can't completely put them together, but I do need to clean it up a little bit. I can either say that that is 4 root 2 minus root 3 all over 2, or I could say the 4 over 2 is 2 root 2, and then minus the root 3 over 2. Comes up, comes down, up. Okay, one last thing that we're going to do today with these radians is another formula that we can use for arc length. You already have the unit multipliers written down in your list. We are used to the arc length is the fraction out of 360 times 2 pi r times the whole circumference, right? If we have our angle in radians, how many radians for the whole circle? 2 pi. Gotta have the pi in there. It's 2 pi radians all the way around the circle. So if I have some number of radians out of the whole circle, and then I multiply that by 2 pi r, or I should have 2 pi here, sorry. My 2 pi's cancel, and that's why I just have the radians times the radius. So if they give you the measure in radians, it's more efficient just to take that times the radius to get how long that part of the circumference is. If they give it to you in degrees, which we'll do on the next example, you can convert it, but I'm not sure that saves any time. So let's do this one last example for the day. If I do this with my new formula, that my arc length is the radian measure times the radius. I have two problems. They give it to me in degrees, not radians, and they give it to me with diameter, not radius. So I have to convert both of them. So to convert the radians, or convert the degrees to radians, I'd need to take the 39.642 degrees, multiply that by the unit multiplier that converts it to radians, need to get rid of the degrees, so that goes in the denominator, and I would need the pi radians in the numerator. And that would give me the radian measure. To change the diameter to the radius, I'd need to take the 7920 and divide that by 2. So then on your calculators, you can do control divided by 39.642 times pi times 7920. Go down to the bottom box and divide by the 180 times 2 or the 360. Let you guys get that punched in on those calculators.
39.858.
Thumbs up, thumbs down, are others of you getting that? And so that would work. Now personally, I think if they give it to you in degrees, in all honesty, I would rather stick with degrees. I would rather say my degree measure out of 360 times 2 pi r, which means I take 39.642 out of 360 times 2 pi, and then I'd still have to do the 7920 divided by 2 for the radius. But isn't that exactly the same thing that I've got here? Because if I take the 2 over the 360, don't I get the 180 that I had up here? And otherwise everything's exactly the same? But to me it's easier if it's degrees, that many degrees out of 360 times circumference, or times area if we're doing a sector. If it's radians, that many radians times the radius if we're doing the arc length, that many radians out of 2 pi if we're doing the sector, and go from there. Anybody with questions on what we've covered today?